We're taking a look today at a paper called Deep Delta Learning, Generalizing Residual Networks with Geometric Transformations. It's by Zhang, Liu, Wang, and Gu.
And this one is a really fundamental rethinking of the identity shortcut, which, is the foundation of almost all modern deep learning.
It really is. So what's the core idea here?
The big innovation is something they call the delta operator, or SSS. It basically takes that rigid, add-only shortcut from a standard ResNet and swaps it out for a learnable geometric transformation.
And that standard connection, that simple plus sign, the authors argue it really boxes the network in. It creates this inductive bias that makes it hard to model anything complex, anything cyclical.
Exactly. Anything that needs negative eigenvalues, think oscillations, competitive dynamics, the standard ResNet just can't do it.
So Deep Delta Learning, or DDL, gets around this by modulating that shortcut path with this new operator, XSS.
Right. And that operator is controlled by two learned things, a direction vector, Dagger, and this really crucial scalar gate, which they call beta.
And that gate is the magic ingredient. It lets the network dynamically choose the geometry of the transformation. It can interpolate between just passing the info through,
Which is identity mapping.
to completely wiping out a feature component,
That's orthogonal projection.
or even flipping its orientation entirely, a geometric reflection.
And by giving the network this geometric control, it can learn much richer dynamics, and maybe more importantly for engineers, it stops this problem of residual accumulation, basically, noise getting stuck and amplified through the layers.
Okay, so let's unpack that. Let's start with the problem itself. ResNets were, a huge breakthrough.
Oh, absolutely. That simple shortcut, Zex plus 1 equals XL plus FXL, it solved vanishing gradients and let us build incredibly deep models.
But when you look at it through the lens of, say, a neural ODE, you see the limitation.
You do. That update is just a forward Euler step with a fixed step size of 1. It's simple, but it's rigid.
And because it's fixed, the Jacobian of that shortcut path is just the identity matrix, permanently.
Exactly. It forces a strong translation bias. The network can only ever add to the features. It can translate them in the feature space, but it can't do these more complex things like rotate them or, crucially, reflect them.
Right. And if you want to model a system where one thing suppresses another, you often need that kind of negative feedback.
Yeah.
Mathematically, that means negative eigenvalues.
Which a standard ResNet just can't realize. The paper cites some earlier work, Grassi et al.
Right.
That really nails this down. If you want to model competition, you need more flexible transitions.
So DDL isn't just a random tweak. It's a principled fix rooted in geometry to solve this very specific rigidity problem.
And to really get it, we have to look at the math, but it's actually pretty intuitive. It all starts with the classic householder reflection matrix.
Okay, a quick linear algebra refresher. The householder matrix, HKKI2KK2, is what you use to reflect a vector across a hyperplane, right?
Precisely. DDL takes that concept but makes it flexible. Instead of that fixed number 2, it plugs in that learnable, data-dependent gate.
So the delta operator becomes AX, I beta x k day.
And that's a rank 1 perturbation of the identity matrix.
Okay, rank 1 perturbation. What does that mean in, plain English?
It means we're only making a change along one single specific direction, the direction kx. Everything else, the entire orthogonal subspace, is left completely untouched. It's like surgical control.
And there's another subtle but really important detail here. The hidden state, sixth error, isn't a vector. It's a matrix.
Right, $6 in or D times dves. This is a key design choice. They're thinking about architectures like transformers, where you have these value matrices. The transformation acts on the feature dimension.
It's designed to slot right into these more complex, stateful models from the get-go.
I think so. Now let's look at the full update rule, because it's not just about changing the shortcut. They do something very clever.
The full update is $6 plus 1 ASCO PECO plus beta XL SSLT.
See that the gate, a beta, it shows up twice. It's applied to the geometric transformation on the shortcut.
Which is controlling what we keep from the old state.
And it's also applied to the constructive term, the part that adds in the new information. They're coupled.
If you rearrange that equation, you get what they call the rank 1 delta form, which is maybe more intuitive. $6 plus 1 plus beta XL V XL V XLT key XL he KXL.
And this form really lays it all bare. That term KATXL a day is the projection of the current state onto that special direction dollars. It's the old memory or the error that needs updating.
So the bit in the parenthesis is the correction signal.
Yeah.
And the whole thing is scaled by beta.
Exactly. And that beta is very carefully constrained to be in the range 0, 2. They use a sigmoid and some scaling to make sure it never leaves that range.
And that range is not arbitrary. It's where all the geometric magic happens.
Yeah.
This brings us to the spectral analysis, which I think is the real aha moment of the paper.
It is. So how does beta control the geometry? It's all in the eigenvalues of that delta operator.
And because it's just a rank 1 change to the identity matrix, the spectrum is incredibly simple.
That's right. KL1 of the eigenvalues are just 1.
Meaning, for almost all directions in the feature space, nothing happens. The features pass straight through, just like a normal ResNet.
Correct. The features in that orthogonal subspace, taper apart, are perfectly preserved, but there's one special eigenvalue left.
And that one is $1 beta.
Yes. And its eigenvector is, of course, the learned direction.
So the whole mechanism is the network learns one specific direction that it needs to mess with, and then it uses the scalar beta to decide exactly how to mess with it. Everything else is left alone.
Yeah.
That's an incredible focusing mechanism.
It is. And if you look at the determinant of the operator, it's just $1 beta. So as soon as beta goes past 1, the determinant becomes negative.
A negative determinant means a change in orientation, a reflection. This is the geometric freedom that the standard identity shortcut could never, ever have.
And we can even talk about orthogonality. The operator is only truly volume preserving, up to sign, if beta is exactly 0 or 2. Anywhere in between, it's actually shrinking the space along that one direction.
Okay, let's walk through the 3 big cases, because this is where it all comes together.
Sure. Let's start with case 1, identity mapping. This happens when beta part goes to 0.
So the special eigenvalue, $1 beta, just goes to 1.
Right. And the operator, eigapar, just becomes the identity matrix. But what's crucial is that because beta also gates the other term, the whole update just vanishes. Second apart plus $1 becomes 60 so.
The layer can be completely skipped. This is great for stability in really, really deep networks.
Okay, case 2, orthogonal projection. This is when beta goes to 1.
Now the eigenvalue, $1 beta, goes to 0.
And the operator becomes ikkt taller. This is a projector. It projects everything onto the subspace that's orthogonal to dollars.
So this is basically a forget gate. It's saying whatever information is aligned with this direction for $1, just zero it out. Erase it.
Exactly. It's a controlled erasure mechanism. It lets the network actively clean its state layer by layer. The operator becomes singular. Its determinant is 0.
And now the most interesting one, the one that unlocks all this new dynamic behavior, case 3, full reflection.
This is when beta Ascari goes all the way to 2. The eigenvalue, $1 beta, goes to Mason 1.
And the operator becomes I2KKTD Tate. We're back to the classic householder matrix.
A perfect reflection across the hyperplane. It's orthogonal, volume preserving, but the determinant is nadish 1. It flips the orientation.
I have to ask the obvious stability question here. If you're allowing reflections and negative eigenvalues, aren't you just asking for trouble? Aren't you risking the very explosions that ResNets were designed to prevent?
That's a great question, and it's why the rank 1 structure is so brilliant. They're not introducing chaos everywhere. They're only allowing that negative eigenvalue along one single dynamically learned direction. The massive orthogonal subspace remains completely stable, with an eigenvalue of 1.
So it's targeted, controlled freedom, not just throwing stability out the window.
Precisely. And this ties directly back to a fundamental concept from memory networks, the delta rule.
Right. If we look at that expanded update rule again, Zaggles plus 1, x bal plus betals, KL, KLT, x dale dale, it looks just like it.
It is. The term KDX is the erase part. It's reading the old memory along direction dollars. Then the whole term in parenthesis is the correction. It's writing the new value dollars after subtracting the old one.
And because the erasure and the injection are happening along the same direction to dollars and scaled by the same geta, they are perfectly coupled.
This synchronous operation gives the network this amazing ability to clean and rewrite specific feature subspaces on the fly, layer by layer.
And this directly attacks that residual accumulation problem. What does that actually look like for an engineer training a model?
It's like feature pollution. Imagine in a deep CNN, some small, noisy artifact gets picked up in an early layer. With a standard ResNet, that noise, or some version of it, just gets carried along layer after layer because you're always just adding. It pollutes the feature maps and can limit how deep you can effectively go.
DDL gives the network a way to say, hey, this feature component along direction gives noise. Let's project it to 0 and replace it with something useful.
And this mechanism isn't entirely new. It's just the application that's novel. The authors point out that this is basically the depth-wise version of what architectures like DeltaNet do over time.
So DeltaNet applies the delta rule to a memory state over time steps, T dollars. DDL applies the exact same rule to a feature activation over depth.
$1. It's a depth-wise isomorphism. Same rule, different axis.
Okay, let's get practical. For someone implementing this, how does it change things like feature mixing? Let's say my input features are totally separate, like a diagonal matrix.
Good question. A standard ResNet would keep them separate on the shortcut path, but DDL forces them to interact. Even with a diagonal input, if you have a non-zero beta, the output feature at index dollars will now depend on the input feature at index j dollar, scaled by this term tkj dollar.
So it induces a controlled geometric coupling between features. That seems really important for complex tasks.
And what if you're not working with matrix states? What if you're just using good old vectors? They call this the scalar value limit.
Right, where dv at a 1 and the state $6 is just a vector $6.
In that case, the update simplifies, but it's still powerful. It becomes a kind of dynamic gating mechanism that's tied to the discrepancy between the target value dollars and the current state's projection onto dollars.
So the update size depends on how wrong the current feature is along that one important direction.
Exactly. It's a localized, discrepancy-based update.
Okay, just briefly on implementation, how do you actually parameterize these new components like the direction dollars?
So K-units has to be robust. They suggest using a small MLP on pooled statistics of $6, or maybe an attention mechanism. The one thing that's non-negotiable is you have to L2 normalize it. It has to be a unit vector for the math to hold up.
And the scalar gate, that needs to be lightweight and bounded.
So a simple linear layer, again on pooled features, passed through a sigmoid and then scaled by 2. That forces it into that 0-2 range.
And the value branch, Vx, that's basically the new FICX there.
Yeah, that should generally match the capacity of whatever your main backbone architecture is. If you're using an FFN block, it should be a similar FFN.
So to sum this all up, ResNet gave us depth by enforcing a very stable but rigid additive dynamic.
And DDL comes in and says, we can have more. It gives us a principled way to add multiplicative geometric control back into the shortcut, letting the network dynamically manage its own layer-wise spectrum.
By allowing things like projection for forgetting and reflection for, changing orientation, DDL lets us build models that are not just stacking layers, but are genuinely learning flexible dynamical systems through their depth.
And that leaves us with a pretty profound question, I think. We know feature accumulation is a problem that limits model depth. So if DDL gives networks the geometric tools to actively fight that, to reflect away noise and reset accumulation layer by layer, can we use this to successfully train stable models that are orders of magnitude deeper than what we can manage today? That's the real promise here.